be our second part of the 3.1 notes for definition of a derivative. And now we are getting into some of the more hands-on stuff with this. We need to graph the derivative of a function of a function f whose graph is shown here on the right, and we want to discuss the behavior of f in terms of the signs and values of f prime. So I have a couple of points labeled here, and if you recall, when we first started talking about derivative is merely the slope. So we are really going to be plotting what the slopes are at each of these points on this function. So I'm going to change my color up here to make something that will stand out a little bit more whenever I graph. So we have A. So what I'm actually going to do here is I'm going to sketch little mini tangent lines, and I'm going to estimate the slope. When you are graphing the derivative, your x values are not going to change. So you can see this A has an x value of 0. So whenever I figure out what the slope is at 0, that is the point that I'm going to plot, but it's still going to be at 0. So I'm actually going to make a table here, x, and then f prime of x. So my first x is about at 0. So if I go through and I sketch the tangent line, I know it's a little bit off because I didn't quite go down into A. But you can see here, this looks like I have about a rise of 2 and a run of 1. So it looks like the slope there is about 2. So this point is going to be 0, 2. And my calibration is just a tiny bit off. I'm sure this will make you feel like you're in class all over again. Okay, so my next one at B, that is about, I would say at about 1.5. It looks like it's almost halfway between the 1 and the 2. And if I look at that slope, that looks to be pretty close to 1. I think it would be fair to say that at 1.5, I have a slope of about 1. So 1.5, 1 will be my next point. 2 is going to be the value for C. That slope is horizontal, so that's going to be 0. So at 2, I'm going to be down here at 0. At D, that is at 3. And it looks like that slope is pretty close to -1. So 3, I would be down at -1. E, that one almost looks like a -1/2. For the slope, 5 would be about the value there. So 5, -1/2. And then at 6, that's my F, and that looks like it has a slope of 0. So you can see here, if we come and sketch this, which it isn't going to be perfect. Let's try that again. I can do that a little bit better. That's going to be a pretty close representation of what your slope actually occurs. I guess if I had drawn the A a little steeper, started up a little higher, it would work out to be a little bit better. But basically, when you are graphing the derivative, you are just looking at the collection of the slope values, like I have here in my table. If you notice, looking at this function, f of x looks very similar to a cubic function. You can see you have the 2 terms there. You have the concave down, you have the concave up. And then over here with our f prime, this one looks very similar to a quadratic function. And again, that's not on purpose. This goes back to the, whenever we take the derivative, the exponent is going to go down by 1. So when you take 1 away from the exponent of a cubic, you get a quadratic. So that does, there's a reason why that works out the way that it does. Our next example, example 4, we are going to sketch the graph of a function that has the following properties. So this one is kind of going backwards from the previous question, because this one, I have the graph of the derivative, and I need to figure out what the original function is. But I also have a few other pieces of information given. So the first piece of information, f of 0 is equal to 0. That is very important because that is going to give me an actual starting point, because this means that the point 0, 0 has to be on my graph. Number 2, the graph of f prime, the derivative of f is shown at the right. So I have this here. Remember, derivative is your collection of slopes. So it's convenient that both of those slopes are horizontal line, or the pieces are horizontal lines, because that means that my slopes are not changing for certain x values. And then number 3, f is continuous for all x. That means that there are no holes in x, there are no gaps, there are no infinite discontinuities. So it's just something to keep in mind. So I'm going to plot this 0, 0 point first, because that has to exist. And now I need to look at the graph of my derivative. So again, this is the graph of the slopes. My slope is at a height of -1 for all the x's 1 and less. My height is at 2, so that means all the slopes greater than 2 are going to be, all the slopes that have an x value greater than 1 are going to have a slope of 2. So 0 would fall right in this left-hand piece with a slope of -1, because that's the height of the piece. So that means I'm going to have a consistent slope of -1 at this value. So slope of -1, that would be like this. And that is going to continue for all the x values. And that slope actually exists the entire way until 1. Once I reach 1, my slope is going to change to a +2. And because of this third statement here, that it's continuous, I know that there is not going to be a gap at the x value of 1. They have to be connected. So starting at this 1, I'm going to be going up 2 and over 1 to get the next part of my graph. So it's going to look like that. You see the one side has a slope of -1. The other side has a slope of 2. Technically, at 1, there, I'm going to write no slope because there is no derivative there, because you have different slopes leading up to it. That's why there's a gap here, and that's why those dots are open, because there is no slope at 1. You're approaching 2 different things as far as your derivatives go, so there is no slope, no derivative at the x value of 1. In your textbook on page 105, it goes over the birthday problem. The birthday problem is a very famous mathematical problem, so I do encourage you to take a look at that, and I'm sure that in the video for the textbook, they are going to talk about that a little bit more, but it is a very interesting problem, so I would like you to look over that. And now we have one-sided derivatives. So if you have a function that is differentiable on some closed interval, has derivative at every interior point of the interval, and your limits have to both exist. So at the endpoints. This is something that we can use to help confirm the existence of something that is differentiable. So just know that this is something that could come up. So you can see this one, if we are approaching 0 from the right-hand side, that would be a right-hand endpoint. If you're approaching 0 from the left-hand side, that's going to be a left endpoint. Okay, so now we have example 6. So we want to show that this has a left-hand derivative and a right-hand derivative, but no derivative at 0 because they're different values. So this kind of piggybacks on what we were looking at with example 5, where you are, I think it might have been example 4, because I think we skipped 5. That was the birthday problem. It's where you did not have that derivative existing at 1. So we are going to look at the left-hand derivative, which will be the top piece, and the right-hand derivative, which is going to be this bottom piece. And I'm going to show that the values are not the same. So 0 is going to be the value that I'm going to use. I don't have to use the letter x for this. we have the limit as h approaches 0 from the left-hand side of 0 plus h squared plus 0 squared all over h. So this would be using this top equation. I'm going to be plugging in 0 plus h for my x value. Well, 0 plus h squared is merely h squared. So I have h squared over h, which when I divide those, I have the limit as h approaches 0 from the left of h, and that's going to equal 0. So my left-hand derivative is 0. My right-hand derivative is 2 times 0 plus h minus 2 times 0 all over h. Because again, I'm plugging 0 plus h. I know this does not look like 0 plus h, but 0 plus h I'm plugging in for the x in the bottom, for the right. So I'm going to have 2 times h plus 0, well, not plus, this should be minus. I'm very sorry about that. I was on a roll too. Okay, smaller. Let's go back and fix that. I know it doesn't really make a difference for this one because it's a 0, but I want to make sure I'm correct there. Okay. So 2 times 0 plus h is going to be 2h. On the bottom, I'm going to have it h. The h's divide out. When you plug in a 0, you're still just left with 2. So my right-hand derivative is 2. My left-hand is 0. Because these are not the same, means there is no derivative at 0. So because they are not the same, there is no derivative at 0. And you could graph these as well. Even though you get the same value at 0, which is 0, it's continuous there, but your slopes are not approaching the same thing. So this adds another layer to that, what we need to check for. And you'll see in 3.2, we're going to look at differentiability. We're going to look at what makes the function be able to take the derivative. So that's one of the important pieces to that puzzle. So lastly, this is your homework assignment. It's already in Schoology. This is something that you should be working on if you haven't already started it. I hope this video was useful. Again, don't just use this one. Make sure you look at the book video as well, because I know that they do much better explanation than I do with some of these things. But hopefully this was useful for you. Let me know if you have any questions or concerns while you're working on your homework, and I'll see you guys later.